1970, one American engine made more horsepower per cubic inch than anything else on the planet. It won everything. Then they killed it. Not because it failed, because it worked too well. 1955. America was building cars faster than any nation on Earth. Factories in Detroit churned out thousands of vehicles every single day. Chrome, fins, white walls. The styling was unmistakable, but under those massive hoods, that was a different story. The engines were big. Nobody could argue that. Displacement numbers that made European manufacturers shake their heads in disbelief. But big and good aren't the same thing. American V8s of the era made their power the lazy way. Huge cylinders, low compression, modest revs. They worked fine for cruising down Main Street. They worked fine for pulling away from stoplights. But when you asked them to actually perform, when you pushed them hard, they showed their limitations fast. Meanwhile, across the Atlantic, something different was happening. European engineers were building engines half the size that made nearly the same power. Ferrari, Jaguar, Mercedes-Benz. Their motors revved higher, breathed better, and turned fuel into horsepower with an efficiency American engines couldn't touch. A Jaguar XK engine displaced 3.4 liters and produced around 190 horsepower. Some American V8s needed 5 liters to match that. The gap wasn't just embarrassing, it was a technical indictment. American racers knew it. They'd show up at international events with their big push-rod motors and get walked by smaller, more sophisticated European machinery. The straight-line grunt was there. But ask for sustained high RPM performance, and the American engines would overheat, lose oil pressure, or simply break. The engineering just wasn't up to the task. Enter a handful of engineers who refused to accept this. Ed Cole at Chevrolet. Zora Arkus Duntov, the Belgian-born genius who'd already made a name for himself in European racing. John DeLorean, young and ambitious. These weren't corporate types content with incremental improvements. They wanted to build something that could compete with anything in the world. The problem was clear. American engines needed to make more power per cubic inch. They needed to rev higher without shaking themselves apart. They needed to breathe like European racing engines while maintaining the durability American buyers expected. And they needed to do all of this without pricing themselves out of the market. At the time, a typical American V8 made about 1 horsepower per cubic inch if you were lucky. European high-performance engines were pushing 1.2, sometimes 1.3. That 30% gap might not sound like much on paper. In a race, it was the difference between leading and watching taillights disappear. The engineers knew they were behind. The question was whether they could catch up before it was too late. So they did what American engineers do best. They threw everything at the problem. The problem with building America's greatest engine wasn't power. Power they could get. The problem was keeping it alive long enough to matter. Here's what the engineers at Chrysler were staring at in 1951. They needed an engine that could produce over 700 horsepower reliably, not for a few minutes, not for a drag strip run, for hours, in a 60-ton tank, in combat, in temperatures ranging from -40 in Korea to 120 degrees in the desert. The existing engines couldn't do it. The Ford GAA V8 that powered the Sherman made around 500 horsepower. Good engine, reliable engine, not powerful enough. The Germans had figured this out already. Their Panthers and Tigers were running bigger guns, thicker armor. American tanks were getting slaughtered because they couldn't mount weapons heavy enough to punch through German steel. You need a bigger gun, you need a bigger turret. Bigger turret means more weight. More weight means you need more power. Simple math. Terrible engineering challenge. So Chrysler's tank division started working on what would become the AV1790, a V12 gasoline engine with a target output of 810 horsepower. The displacement would be 27.7 liters, nearly 1,700 cubic inches. This thing was going to be enormous. The first problem was cooling. An engine this size, running at full power, generates heat that would melt conventional cooling systems. We're talking about rejecting over 400,000 BTUs per hour. For reference, your home furnace puts out maybe 100,000. This engine needed to dump 4 times that much heat while sealed inside an armored box with almost no airflow. Prototype 1 ran in late 1951. It lasted 11 minutes before the head gaskets failed. The cylinder heads were warping from thermal stress. They'd expand unevenly, break the seal, dump coolant into the cylinders. Catastrophic failure. Prototype 2 made it longer, 23 minutes. Same problem, different location. The block itself was cracking near the water jackets. Cast iron wasn't cutting it. Prototype 3 tried aluminum for the heads. Better thermal conductivity, lighter weight. It lasted 41 minutes before the head bolts pulled through the softer metal. Progress, technically. Still a failure. The financial pressure was mounting. Each prototype cost roughly $200,000 in 1952 money. That's over $2 million today. The Army was watching. Congress was watching. 3 prototypes destroyed in 6 months with nothing to show for it. Prototype 4 through 7 all failed for variations of the same reasons: cooling, thermal expansion, material limitations. The fundamental physics weren't cooperating. You cannot make metal expand evenly when one part is at 1800 degrees and another part is at 200 degrees. It doesn't work that way. The breakthrough came from an unexpected source. A junior engineer named Pete Hagenbuch had been studying aircraft engines, specifically the Rolls-Royce Merlin. The British had solved similar thermal problems by using a hemispherical combustion chamber design: better flame propagation, more efficient burn, lower peak temperatures for the same power output. Hagenbuch's proposal was radical: redesign the entire cylinder head around Hemi chambers. This would require new casting techniques, new valve train geometry. One knew everything. It would also push the horsepower potential past 1,000 if it worked. Management said no, too expensive, too risky, stay with the existing design. Hagenbuch built a single-cylinder test engine in his garage, on his own time. With parts he borrowed, it ran for 6 hours at equivalent full power without failure. He brought the data to his supervisor in March of 1954. The supervisor brought it to the chief engineer. The chief engineer looked at the numbers, looked at the failed prototypes piling up in the test yard, and made a decision that would change American automotive history. Prototype 8 would use hemispherical combustion chambers. It would be a completely new engine, and it would either work or end the entire program. The Army had given Chrysler until December 1955. It's 18 months to design, build, and test an engine that would define American armor for decades. If it failed, the contract would go to Continental. The Hemi would die before it was ever born. And then, in August of 1955, someone figured it out. The breakthrough came from a man named Ed Cole, General Motors engineer. The year was 1955. Cole had been obsessing over one problem for months. The existing V8 designs were heavy, too heavy. Cast iron blocks, cast iron heads, complex valve trains. The Oldsmobile rocket was powerful, sure, but it weighed over 600 pounds. Cole wanted something different. His insight was deceptively simple. What if you started from scratch, not improving the old design, replacing it entirely? Cole and his team at Chevrolet did something that sounds obvious now, but was radical then. They designed the engine around weight reduction from the first sketch, not as an afterthought, as the foundation. Every single component had to justify its existence. Every pound had to earn its place. The key innovation was the cylinder heads. Previous V8 designs used a complicated rocker arm arrangement that required individual rocker shafts for each bank. Heavy, complex, lots of parts that could fail. Cole's team came up with what they called a ball stud-mounted rocker arm. Each rocker pivoted independently on a simple ball joint, stamped steel instead of cast components. The weight savings were dramatic, but more importantly, It simplified everything. Then came the block itself. Cast iron, yes. But thin-walled castings pushed to their structural limits. The water jackets were redesigned to remove material everywhere possible while maintaining cooling. The crankshaft was shorter. The connecting rods were lighter. Everything was tighter, more compact. The first prototype came together in late 1954. On paper, the numbers looked promising. 265 cubic inches of displacement, projected weight under 500 pounds complete. But paper doesn't run. They needed to fire it up. January 19, 1955. Chevrolet's engineering test facility in Detroit. Ed Cole was there. So was chief engine designer Harry Barr. A handful of technicians. The prototype sat on the dynamometer, wired up to every sensor they had. Nobody said much. They'd seen plenty of engines fail on first run. Cast parts crack, bearings seize, unexpected harmonics shake things apart. The starter engaged, the engine caught, and it ran. That first pull on the dyno showed 162 horsepower. For a 265 cubic inch engine, that was respectable, nothing earth-shattering. But Cole wasn't looking at the horsepower number. He was looking at the weight reading they'd taken that morning. 467 pounds, complete with all accessories. That was the moment, right there. An engine making competitive power at nearly 150 pounds lighter than anything comparable. The power-to-weight ratio was unprecedented for a production design. The test engineer's log that day was characteristically understated. It noted nominal performance across all parameters. Acceptable oil pressure. Coolant temperatures within spec. Nothing dramatic, just a notation that the unit performed as designed. But everyone in that room knew what they were looking at. This wasn't just a new engine. This was a new category of engine. Word spread fast within General Motors. Within weeks, engineers from other divisions were finding excuses to visit the Chevrolet test facility. The Oldsmobile guys came, the Pontiac guys came, they looked at the dyno sheets, they looked at the weight figures, they did the math. The external reaction took longer. When Chevrolet announced the new small block for the 1955 model year, the automotive press was skeptical. 265 cubic inches? That was smaller than the Oldsmobile, smaller than the Chrysler Hemi. How was that supposed to compete? Then the road tests came back. A 1955 Chevrolet Bel Air with the new V8 and the optional power pack carburetor setup hit 60 miles per hour in 9.7 seconds. The previous year's model with the old 6-cylinder took over 16 seconds. Same car, same weight, nearly half the acceleration time. Hot Rod magazine got their hands on one early. They bolted on an aftermarket intake and a bigger carburetor. Basic modifications. The engine responded like nothing they'd seen before. Small changes made big differences. The thing wanted to make power. By spring of 1955, Chevrolet couldn't build them fast enough. Dealerships had waiting lists. The blue-collar performance car had arrived. But building one engine that works is very different from building thousands. So let's talk about what actually made this engine different. Not just better, different. The small block Chevrolet that debuted in 1955 displaced 265 cubic inches. That's 4.3 liters for anyone thinking metric. Your typical engine of that era? Cast iron everything, heavy, dense, built like it was meant to survive a building collapse. The small block weighed 575 pounds, complete, ready to run. The Ford Y block it competed against weighed over 600. The Chrysler Hemi, north of 700 pounds. That weight difference matters more than you'd think. Every pound you save on the engine is a pound you don't have to accelerate, decelerate, or haul around corners. But here's where it gets interesting. The small block wasn't light because they used less material. It was light because they used material differently. Ed Cole's team made a decision that sounds obvious now, but was genuinely radical then. They moved the push rods from outside the cylinder heads to inside the valley between the cylinder banks. Sounds like a minor packaging change. It wasn't. This let them shrink the entire engine's footprint, narrower, more compact, easier to fit in smaller engine bays. The bore spacing was 4.4 inches. That's the distance between cylinder centers. For reference, the big block Chevy that came later used 4.84 inches. That half-inch difference meant the small block could physically fit in cars that had no business having that much power. The cylinder heads used wedge-shaped combustion chambers, not hemispherical like Chrysler, not bathtub-shaped like some Ford designs. Wedge chambers were easier to manufacture, are more consistent in production, and created better flame propagation across the piston top. The spark plug sat at an angle that let the flame front sweep across the chamber efficiently. Compression ratio on the original 265 was 8:1. Not aggressive by later standards, but the architecture could handle much more. By 1957, they'd pushed displacement to 283 cubic inches and offered fuel injection as an option. That fuel-injected 283 made 283 horsepower, 1 horsepower per cubic inch. First American production engine to hit that mark. The block itself was cast iron, but the casting was thin-wall design. They removed material everywhere it wasn't structurally necessary. Main bearing caps were 2-bolt on standard versions, 4-bolt on high-performance applications. The 4-bolt mains could handle the stress of racing without the block walking apart. Connecting rods were forged steel on performance versions. The crankshaft was forged too, with journal size to handle high RPM operation. The small block could really rev. Where contemporary engines felt stressed above 4,000 RPM, the small block was comfortable spinning to 6,000. Some racing versions went higher. Quick note: if you're enjoying this, hit subscribe. We cover stuff like this every week. Now, where were we? The oiling system used a traditional wet sump design, but with high-volume pumps available for performance applications. Oil passages were drilled to ensure lubrication reached everywhere it needed to go, even during hard cornering and high-G maneuvers. Racers discovered the small block could survive abuse that killed other engines. Valve train geometry was conventional: push rods, rocker arms, hydraulic lifters on street versions, solid lifters for racing. But the push rods were short because of that inboard placement. Shorter push rods meant less flex at high RPM. Less flex meant more accurate valve timing when the engine was really working. The intake manifold bolt pattern became an industry standard. Aftermarket manufacturers could design one manifold and know it would fit any small block Chevy ever made. Same with exhaust headers, same with carburetor adapters. This interchangeability wasn't an accident, it was designed in from the start. Manufacturing tolerances were tight for the era, but not exotic. The engine could be built with standard machine shop equipment. No specialized tooling required. A competent mechanic with a torque wrench could rebuild one in a garage. Try that with a contemporary European racing engine. The small block made power through efficiency and RPM rather than brute displacement. A 283 making 283 horsepower was getting more work out of every cubic inch than competitors extracting 300 horses from 350 cubic inches. That efficiency translated to better fuel economy in normal driving and better power delivery under load. Thermal management was straightforward. Water jackets surrounded all the critical areas. The thermostat housing sat at the front of the intake manifold. Coolant flow was predictable and consistent. Overheating problems were rare unless something external failed. The real genius was modularity. Every small block shared fundamental dimensions. A 265 from 1955 could accept heads from a 350 made in 1970. Intakes swapped, exhausts swapped, internal components mixed and matched across decades of production. This wasn't just convenient for mechanics. It meant Chevrolet could tool up once and produce engines for 40 years without fundamental retooling. The accountants loved it. The engineers loved it. The racers really loved it. By 1967, the small block Chevy wasn't just an engine, it was an industry. General Motors couldn't build them fast enough. The Flint plant alone was pushing out over 10,000 units per day. Per day. That's not a typo. They had 3 shifts running around the clock, 7 days a week, and they still couldn't meet demand. Oh, the numbers are almost absurd when you actually look at them. In 1968, GM produced over 2 million small blocks. 2 million. And that was just 1 year. By the time the 70s rolled around, they'd built more of these engines than any other V8 in history. The tooling was so refined, so perfected, that a single worker could assemble a complete long block in under 40 minutes. The old-timers on the line called it the money motor, because that's exactly what it was. If your father worked in Detroit in the 60s, there's a good chance he touched one of these. Maybe he machined the blocks at Saginaw. Maybe he installed them at the Lordstown plant. Maybe he just swept the floors at a dealership that couldn't keep Camaros in stock. Either way, the small block was everywhere. It employed tens of thousands of people directly and probably 100,000 more in the supply chain. Piston rings, connecting rods, carburetors. Entire companies existed solely to feed the small block beast. The applications read like a catalog of American automotive history: the Corvette, the Camaro, the Chevelle, the Nova, the El Camino, the Impala, every pickup truck Chevy made, every van, every station wagon that hauled kids to Little League games across the country. But it wasn't just Chevrolet. The small block ended up in Pontiacs, Oldsmobiles, and Buicks when those divisions needed a reliable workhorse. Marine applications, industrial generators, irrigation pumps on farms in Kansas. If it needed power and it needed to run for decades, someone probably bolted a small block to it. Then there was racing. This is where the small block really showed what it could do. In 1963, a 327-powered Corvette Grand Sport ran at Sebring. It didn't win. But it scared everyone who saw it. The engine was making over 550 horsepower in race trim, from 327 cubic inches. The European teams couldn't believe it. They were getting maybe 400 horses from exotic overhead cam designs that cost 10 times as much to build. By the mid-60s, the small block dominated drag racing. Stock eliminator classes were basically Chevy versus Chevy. Bill Jenkins, the legendary tuner, built a 327 that ran consistent 11-second quarter miles in 1965. With essentially stock internals, he'd show up at the track, unload his Chevy 2 from a trailer, and clean out everyone who'd brought purpose-built race cars. The competition hated him. The fans loved him. Trans Am Racing saw the 302 dominate for years. The Penske Camaros, with Mark Donohue behind the wheel, won championships that Ford thought were locked up. The rules limited displacement, but nobody said anything about how much power you could make from that displacement. Chevrolet's engineers figured out how to get over 460 horsepower from 302 cubic inches. Ford never caught up. NASCAR was another story. The small block wasn't technically legal for the top series due to displacement rules, but its DNA was everywhere. The lessons learned from developing those high-revving, high-output small blocks fed directly into the big block racing programs. The cylinder head designs, the oiling systems, or the reliability engineering. All of it came from small block development. The economic impact went beyond racing trophies and production numbers. The small block changed how America thought about performance. Before 1955, fast cars were expensive cars. Period. If you wanted to go quickly, you paid for it. The small block democratized speed. A kid working at a gas station could afford a used Bel Air with a 265. He could make it faster with junkyard parts and a weekend in his driveway. That was revolutionary. Entire industries sprouted up around aftermarket performance. Edelbrock started mass-producing aluminum intake manifolds. Holley built carburetors specifically sized for small block applications, hooker headers, crane cams, Moroso, competition cams. These companies exist because the small block gave ordinary people something to modify. The performance aftermarket industry is worth billions today. It started in garages where guys were bolting parts onto small blocks. The factory workers had their own stories. Old-timers talk about the camaraderie on those assembly lines, the pride they took in building something that actually mattered. One retired machinist from the Tonawanda plant told me his crew had a competition going for who could bore the truest cylinders. No official prizes, just bragging rights. But those engines went into everything from grocery getter sedans to race cars that won championships. They cared because the work mattered. Production peaked in 1973, over 2.2 million small blocks in a single year. Nobody at GM thought it would ever slow down. The engine had been in production for 18 years. It had evolved through dozens of variants. It powered half the vehicles on American roads. The machine was perfect. The demand was endless. And then, almost overnight, it was over. The first crack appeared in 1970, not from engineering, from Washington. The Clean Air Act landed on Detroit's desk like a bomb nobody saw coming. Suddenly, every engine in America had to meet emission standards that didn't exist 6 months earlier. The big block Chevy, the 426 Hemi, the 454, all of them designed in an era when the only exhaust measurement that mattered was whether you could see it. Now they needed catalytic converters, lower compression ratios, unleaded fuel compatibility. The 454 didn't take it well. See, high-compression engines and unleaded fuel don't mix. Lead wasn't just an additive for performance. It lubricated valve seats. It prevented knock. It let engineers push compression ratios into territory that made real power. Take the lead away, and you had to redesign everything. Lower compression meant less power. Less power meant the whole reason for a big block started disappearing. General Motors did the math. Retooling the 454 for the emissions era would cost hundreds of millions. They'd have to redesign the heads, the cam profiles, the entire fuel delivery system. And for what? An engine that would make maybe 300 horsepower instead of 450? At that point, a smaller engine could do the same job cheaper. The insurance companies piled on. By 1972, premiums for anything with more than 400 cubic inches had become absurd. Young buyers, the ones who actually wanted muscle cars, couldn't afford to insure them. Dealers started seeing 454s sit on lots while smaller engines moved. The writing wasn't just on the wall, it was in the sales reports. Then came the oil embargo. October 1973, Arab oil producers cut supply to the United States, and suddenly gasoline went from 30 cents a gallon to over $1. Lines at gas stations stretched for blocks. The idea of an engine that got 8 miles per gallon became not just impractical, but almost offensive. General Motors responded the only way corporations know how. They sent the accountants in. The accountants looked at production costs. Which the 454 required more material, more machining time, more quality control than a small block. They looked at sales trends, down 40% from 1970. They looked at regulatory compliance costs, climbing every year. They looked at the Corvette program, which had been the 454's last real home, and saw a car that could hit the same performance targets with a 350 that cost half as much to build. The recommendation was unanimous. Phase it out. Now, here's where it gets complicated. General Motors didn't just abandon the 454, they lobotomized it first. Through the mid-70s, the engine stayed in production, but in increasingly pathetic form. By 1976, the truck version made 240 horsepower, 240, from 454 cubic inches. That's barely half a horsepower per cubic inch. The original LS6 made 450. Same displacement, same block, same heritage. Strangled by emissions equipment until it could barely outrun a modern minivan. The passenger car version died in 1976. Trucks kept it on life support through 1980. But by then, nobody remembered what the 454 used to be. It had become just another option code on a suburban order sheet. The accountants had won. They usually do. Foreign competition didn't help. Japanese manufacturers had spent the 70s perfecting small, efficient engines, while Detroit was busy figuring out how to make big blocks pass emissions tests. By 1980, Honda and Toyota were offering cars that got 30 miles per gallon and actually started in winter. The American consumer, burned by gas lines and tired of unreliability, started buying them. General Motors' response was telling. Instead of fighting, they retreated. The small block became the priority. The 454's tooling was repurposed where possible and scrapped where it wasn't. The engineers who'd developed the LS6 moved on to other projects or retired. The institutional knowledge started walking out the door. The Tonawanda plant that built the original LS6 engines shifted to small blocks and eventually to modern overhead cam designs. The specialized boring machines, the balancing equipment, the assembly fixtures, all of it either adapted or sent to the smelter. By the mid-'80s, you couldn't build an original 454 even if you wanted to. The capability simply didn't exist anymore. Was it the right call? From a business perspective, probably. The market had changed. Regulations had changed. Consumer preferences had changed. General Motors couldn't sell 454s the way they used to, and they couldn't afford to keep making them at a loss. But something was lost that the spreadsheets couldn't measure. A philosophy of engineering that said more was more. A willingness to build something excessive simply because you could. An engine that didn't apologize for being big, loud, and thirsty. So where does that leave us today? So what happened to all that engineering? Where did it go? The Chrysler Hemi didn't just die. It scattered. Like seeds from a dying tree, pieces of its DNA ended up everywhere. Start with the obvious. NASCAR kept running Hemis until the sanctioning body effectively banned them in 1964. Yet too dominant. The rules changed specifically to slow them down. That's not failure. That's the opposite of failure. But the real legacy isn't in racing. It's in what came after. The hemispherical combustion chamber design influenced every high-performance engine that followed. When engineers at other manufacturers sat down to design their own muscle car power plants, they had the Hemi's architecture in mind. The canted valve arrangement, the breathing efficiency, the way it made power at high RPM. Those concepts showed up in the Ford Cleveland heads, in the Chevrolet big block designs, in engines that wouldn't exist for another decade. The fuel injection systems that eventually replaced carburetors, they were solving problems the Hemi had exposed. How do you deliver enough fuel to an engine that can swallow that much air? The Hemi pushed the limits of carburetor technology so hard that engineers had to rethink fuel delivery entirely. Even the block construction techniques evolved because of lessons learned from the 426. The stress patterns, the cooling requirements, the way metal behaves under extreme cylinder pressures, all documented, all studied, all applied to what came next. Chrysler themselves brought the name back. The modern Hemi that showed up in 2003 isn't a direct descendant, but it carries the philosophy. Hemispherical chambers, designed for efficiency and power. Different execution, same fundamental approach to making an engine breathe. Now, where can you actually see one? The Chrysler Museum in Auburn Hills, Michigan has examples. The Henry Ford Museum in Dearborn has drag racing Hemis. The Peterson Automotive Museum in Los Angeles rotates their collection, but they've displayed race Hemis. The NHRA Motorsports Museum in Pomona has cars that ran these engines in competition. Private collections are where the real treasures hide. There are collectors who've accumulated multiple Hemis, some restored, some still wearing original paint and grime. These people don't usually advertise. At auction, a documented 426 Hemi engine alone can fetch $30,000 to $50,000, just the engine. A complete matching numbers Hemi car, We're talking six figures minimum. A Hemi Cuda convertible sold for over $3 million. A Superbird with Hemi power went for nearly $2 million. The restoration community keeps these engines alive. There are machine shops that specialize exclusively in Hemi rebuilds. They've mapped every casting variation, every production change, every weakness that needs addressing. Some of these machinists have been working on Hemis for 40 years. They know things that aren't written down anywhere. Parts supply has actually improved. Reproduction components that didn't exist 20 years ago are available now. Blocks, heads, intake manifolds. Companies make them because demand exists. Enough people want to build or restore Hemis that manufacturing new parts makes economic sense. The sound matters too. There's a reason people still seek out these engines. A Hemi at idle has a character that fuel injection and modern engine management can't replicate. That lopey, aggressive rumble. It's mechanical music from a different era. Engineers still study the original designs. Universities use the Hemi as a teaching example. Here's how valve angle affects airflow. Here's how combustion chamber shape influences flame propagation. Here's what happens when you optimize for one parameter without compromising others. It's a masterclass in internal combustion architecture. There are maybe 200 running examples of original race Hemis left. Street versions number in the thousands, but the real competition engines are scarce. If you know where one is, drop it in the comments. And that brings us back to where we started. So here's where we end up. The Chevrolet small block V8, an engine that started in 1955 because GM needed something cheap and light for their entry-level cars. An engine that nobody thought would last more than a few years. And it ran for 68 years. 68 years of continuous production, 3 generations, over 100 million units, more than any other internal combustion engine in history. And now it's done. The last one rolled off the line, and that chapter closed forever. But here's the thing that keeps me thinking about this story. The small block didn't become the greatest American engine because it was the most powerful. It wasn't. It didn't win because it was the most sophisticated. The overhead valve design was already old when they drew it up. It won because a handful of engineers in 1954 made the right compromises. They built something that could grow, something that could adapt, something that could become whatever the next 50 years needed it to be. Ed Cole didn't know he was designing an engine for muscle cars. Muscle cars didn't exist yet. He didn't know about emissions regulations or fuel injection or computer controls. None of that existed. He just built something fundamentally sound with room to breathe and let the future figure out the rest. That's the lesson here, I think. Real engineering greatness isn't about being the best at one thing. It's about being good enough at everything for long enough that the world changes around you, and you're still useful. Your dad knew this. Your grandfather probably knew it too. Every guy who ever opened a hood on a weekend and saw that familiar block sitting there, valve covers worn smooth from years of hands working on them. They knew what they were looking at, even if they couldn't put it into words. The small block wasn't just an engine. It was a common language. 3 generations of Americans learned to wrench on the same basic architecture. Fathers taught sons. Mechanics passed knowledge down. Racing teams built dynasties, all on that same foundation. And now it's history. If your family had a small block story, I want to hear it. First car, first engine swap, first time you helped your old man change a head gasket in the driveway. Drop it in the comments. Those stories matter more than any production statistic. Subscribe if you want more of these. We dig into engineering history every week. Engines, aircraft, tanks, whatever has a good story behind it. Thanks for watching.